Benthic communities play an important role in maintaining the integrity of marine ecosystems. The presence of benthos contributes greatly to the maintenance of biodiversity as it provides complex and diverse habitats for other organisms and increases food supply. Tropical archipelagos such as the Philippines include extensive reef systems that house diverse organisms. However, these reef systems have incurred severe declines in coral reef health primarily due to poor land use practices, rapid coastal development, overfishing, and destructive fishing. As a response, marine protected areas were established in the Philippines to counteract these prevalent threats. In the benthos, interactions between biotic and abiotic components balance and shape the ecosystem. These intricate relationships guarantee the efficient movement of energy and nutrients. Hence, by studying the dynamics and interrelationships among benthic life forms, the condition of the ecosystem can be better understood, from which better management and conservation strategies may be formulated. This study was conducted with the following objectives: to identify benthic composition and benthic cover, determine and characterize dominant coral forms and algal groups, determine interrelationships among benthic type forms and abiotic substrates, assess substrate stability and determine percent cover of stable and unstable substrates for coral settlement, assess coral ecological condition using coral mortality index and bioerosion ratio, infer possible anthropogenic and natural processes or disturbances responsible for the observed patterns and relationships, and finally, formulate a management and conservation plan for Matarinao Bay.
For the methods, the survey area is located in Matarinao Bay, Eastern Samar, Philippines. Matarinao Bay covers an area of 7,500 hectares with a coastline of more than 40 kilometers. Due to increasing concerns regarding the environmental condition and the status of its coastal resources, a need to assess the composition of marine communities within these areas was brought to attention. This study covered 14 stations within and outside the four marine protected areas that are situated in three municipalities: San Miguel and Hernani, Minalongan and General MacArthur, and Bulawan and Dio Island in Salcedo. For the data collection, the Manta-Tow survey and point intercept transect method, as suggested in the Coral Reef Monitoring Manual by Oichauco et al. 2010, were employed in this study. Assessment of corals and other benthos at a chosen level of categories was done using the Manta-Tow survey, a broad-scale monitoring to cover a large area at lower resolution to have a general idea and offer an estimate of the samples present in the area. After the Manta-Tow survey, point intercept or the line transect method, a medium-scale monitoring which covers a higher resolution, was performed to have a more detailed information of the benthic cover and composition in the area. The observed benthic components are categorized into abiotic, algae, dead corals, hard corals, other fauna, soft corals, and sponges. Hard corals are further classified into various coral forms. Abiotic is further divided into the substrate types. Lastly, algae are divided into four algal groups. Shown in Table 1 are the codes used for specific benthic life forms and their corresponding meanings and category. The initial analysis of the raw data was done as recommended in the Coral Reef Monitoring Manual. First, a pivot table containing the total score for all life forms and categories in all sites was generated. The average percent covers of all benthic categories in Matarinao Bay were then calculated. Using the data, a pie chart was created to show both the benthic composition and benthic cover. Based on the percent covers calculated, the relative proportion of the percent covers of dominant coral forms, algal groups, and substrate types were all calculated separately. The data were then presented graphically using a stacked column bar chart. To identify the relationship between the different benthic groups and life forms, persons correlation tests were conducted using the percent covers. Relationships within and between the benthic groups were assessed. The significance of the correlation coefficients was also tested by comparing it to a critical value. For the assessment of substrate stability, percent covers of stable and unstable substrates for coral settlement were determined using the formula shown. Moreover, the percent cover were also correlated with other benthic groups to observe trends. The coral mortality index and bioerosion ratio were calculated using the formula shown. The CMI and bioerosion ratio were compared among the different sites. Then, these were also correlated with other variables. Linear regression tests were conducted and a scatter plot was also generated to show the trends and relationships visually. Adapted from Zamani and January in 2020, the rock mortality ratio and bioerosion ratio were categorized from values 1 to 4 using the guide in Table 2. The ecological condition of the coral reefs in different sites are then assessed using the sum of the values of mortality and bioerosion, which ranges from 0 to 8. The mortality bioerosion index values were interpreted using the guide shown in Table 3. Figure 2 shows the benthic composition and benthic cover observed in Matarinao Bay, Eastern Samar in 2019. The majority of the benthic community is covered by algae, followed by hard corals and dead corals. Less than 1% of the benths are covered by other biota such as soft corals, sponges, and other fauna. The rest and majority of the area is covered by abiotic substrates. Abiotic substrates and algae are more dominant compared to hard corals by 9% and 4% respectively. Healthy coral reef ecosystems are dominated by reef-building corals or hard corals. However, other non-hard coral benthos such as algae may outcompete hard corals due to various factors such as seasonal changes, overfishing, nutrient influx, and coastal development. Based on the benthic composition and cover of Matarinao Bay, a coral to algal shift was observed. This shift from coral to algal dominance posed a threat to corals. The relatively higher value could indicate lesser or absence of limiting factors such as interspecific competition, grazing herbivores, and other abiotic factors that plays a role in maintaining reef health. Moreover, the observed higher abiotic substrate could indicate possible occurrence of sedimentation in Matarinao Bay, which could pose a threat to coral growth and reproduction. Figure 3 shows the relative percent cover proportion of dominant coral forms, algal groups, and substrate types. Massive corals composed almost 62% of the total hard coral cover, followed by branching and encrusting corals. Other coral forms include branching acropora, table acropora, foliose, mushroom, and submassive. Coral reefs, especially branching species, have shown to suffer impacts of typhoons. Massive coral forms could have dominated in all sites because of its stable structure compared to branching corals. However, the results of the survey portrayed the slow growth and vulnerability of the coral species following the effects of Super Typhoon Yolanda in 2013. Moreover, most reefs and patches have been reported to have already suffered degradation prior to Super Typhoon Yolanda, which may also explain the poor live coral cover up to date despite considering Matarinao Bay as a marine protected area. Algae present in Matarinao Bay are dominated by algal assemblages. Common components of these assemblages are macroalgae and turf algae. The increase in macroalgal cover could be influenced by biotic factors such as herbivore grazing and competition, and abiotic factors such as temperature, light, and nutrients. Higher cover of macroalgae and lower coralline algae cover, as observed in Matarinao Bay, are early indicators of ocean acidification due to climate change, as similarly observed in the Great Barrier Reef. High sand and silt cover indicates occurrence of sedimentation or siltation due to land-based activities.
The succeeding tables depict relationships between and within different benthic groups using Pearson's correlation. For the Pearson's correlation, an absolute value of 1 indicates a perfect linear relationship, while a correlation value close to 0 indicates no linear relationship between the variables. This table shows the Pearson's correlation between hard coral cover and various coral forms. In general, there is a positive correlation between the hard coral cover and different coral forms. Higher hard coral cover increases the chances of individuals that may be able to spawn. Higher number of various coral forms increases larval production for each form, resulting to a higher hard coral cover. The next table shows the correlation within different algal groups. This table shows a positive correlation between algal cover and the three algal groups, namely algal assemblage, macroalgae, and turf algae. Similar to corals, abundance of algae could also be attributed to the number of algal propagules being produced by the existing algal cover and groups, coupled with other disturbances. In contrast, only coralline algae depicted a negative correlation with the other algal groups. This table shows the correlations within the abiotic substrate. A significant negative relationship between sand and rocks was observed with an R value of 0.794. Table 7 shows the relationship among various hard coral forms with other biota such as soft corals, algae, and other fauna. A significant negative correlation was observed between hard corals, specifically massive corals, and algal assemblage. Several studies show that algal dominance could inhibit coral larval settlement and survival because of the increased competition for space and resources, and also an increase in incidental predation. However, there is a significant positive relationship between massive corals and coralline algae. Coralline algae promote coral settlement by providing important cues. This could explain the positive correlation between hard corals and coralline algae, and the negative relationship between the coralline algae and the other three algal groups. Table 8 shows the relationship among various hard coral forms with dead corals and abiotic substrates. Hard corals and branching corals are positively correlated with dead corals shown in the second column. Higher hard coral cover exposed to disturbances, especially branching corals, results to higher dead coral cover. To add, corals are also subject to predation by COTs or crown of thorns, known to be one cause of coral deaths. In general, hard corals are positively correlated with rocks, particularly encrusting corals with an R value of 0.851. Rocks provide a relatively stable substrate, thus the positive correlation with hard corals. On the other hand, the presence of rubble, sand, and silt has been reported as a strong negative predictor of juvenile coral density because of its low stability. Corals experience high post-settlement mortality on these unconsolidated surfaces due to its constant movement. As shown in the third column, the hard corals are negatively correlated with the overall abiotic substrate because the substrate was mainly composed of sand and silt, which are considered unstable substrate. Some studies showed that rubble is an important factor in the coral settlement, providing physical cues, and also has sedimentological roles, providing the raw material that infills inner reef, creating new and different habitats. This could explain the positive correlation between rubble and the hard corals. The next table shows the relationships among algal groups with dead corals, other fauna, and abiotic substrates. A strong negative relationship between algae and dead corals was observed. Among the algal groups, only coralline algae produced a positive relationship with dead corals. Algal assemblages are found to be positively correlated with silt, but negatively correlated with rubble. Weak negative relationship between turf algae and abiotic substrates, particularly silt and rubble, was also observed. This is in contrast to the observed positive relationship between turf algae and sediments in some studies wherein turf algae often accumulate sediments. Increased sediment levels could also be associated with increased nutrient levels, which supports algal growth. Several studies positively correlate the increases in the cover of turf algae and macroalgae with environmental nutrient levels. Moreover, increased sediments inhibit feeding rates of some herbivorous species, which, as a result, algal development and dominance are enhanced.
Stable substrates for coral settlement include coralline algae and rocks, while unstable substrates include sand, silt, and rubble. As seen in the figure below, majority of the substrates in all sites are unstable for coral settlement, where the highest cover of unstable substrates was observed in San Miguel inside and the lowest in Dio Island outside. Very low stable substrate cover is only found in Manalongan inside and Dio Island inside and outside. Hard coral cover showed a positive correlation with stable substrate, indicating that higher coral cover is observed in thriving areas with stable substrate. Additionally, this relationship is also supported by the negative correlation between hard corals and unstable substrate. Corals require a hard, cemented substrate like rocks for stable settlement. However, as these results indicate, the dominant abiotic groups are unstable substrates such as sand and silt. The high levels of sand and silt may impede coral growth and could even degrade reefs if present in abundance, which is why it is necessary to address this concern to prevent further detriment to the reefs in this benthic community. Coral mortality index is the ratio of dead corals to the sum of hard and dead corals, with the lower index values indicating better reef conditions. In Matarinao Bay, the highest CMI was observed in San Miguel as a result of having the lowest percent of live coral cover. The lowest CMI is in Bulawan outside, which is attributed to its low dead coral cover at 6.18%. Others fall on the average of 0.3 to 0.4 despite having a relatively higher percent of live coral cover, which is due to the corresponding relatively higher percent of dead coral cover. In addition, the CMI values obtained were also positively correlated with the substrate percent cover. CMI showed a strong positive correlation with unstable substrate. As mentioned earlier, sand contributes to coral mortality as it can smother and kill the corals. Also, suspended sand and other sediments can increase water turbidity, resulting in reduced light penetration and lower photosynthetic activity of symbiotic zooxanthellae. Despite the competition between algae and corals, there is no significant relationship between CMI and algal assemblage cover.
The bioerosion index is the ratio of hard corals and sum of hard corals and all other biota. Higher index means lower competition and less likely that hard coral to non-coral builder shift will occur. Lower index indicates higher competition and higher chance of phase shift. As seen on the figure on the left of the slide, Dio Island inside had the highest bioerosion ratio of 0.86, while San Miguel inside had the lowest of 0.12. There is a higher bioerosion ratio within all MPAs, which indicates lower competition between hard corals and other biota. The non-NPA sites are more prone to hard coral to non-hard coral shift. As shown on the linear regression figure, there is positive relationship between bioerosion ratio and hard corals. This is because the index measures the dominance of the hard corals. Moreover, among the other biota, the algae have the greatest impact on bioerosion index. There is a significant negative relationship between bioerosion index and algal cover. This is supported by the negative relationship between hard corals and algae. Finally, there is no significant relationship between the bioerosion index and the percent cover of soft coral, sponges, and other fauna. This is due to the small number of these organisms. With the raw mortality ratio and bioerosion ratio adapted from a study by Zamani and Zenwar in 2020, the Mortality Bioerosion Index or MBI considers the impact of these two processes on the coral reefs. As shown on the table, Matarinao Bay is in a good condition with an MBI of 5. The two sites, both in the MPAs Dio Island and Bulawan, are in excellent condition, and 3 of the sites including Minalongan Inside, Bulawan Outside, and Bio Island Outside are in good condition with an MBI of 6, while Minalongan Outside and San Miguel Inside are in poor condition with an MBI of 3. As shown on the two tables on the right side of the slide, the results were categorized from values 1 to 4 using the guide in Table 2. The ecological condition of the coral reefs in the different guides are then assessed using the sum of values of mortality and bioerosion, which ranges from 0 to 8. The mortality bioerosion index values were interpreted using the guide shown in Table 3. The coral sites that obtained very poor and poor outcomes are associated with low light intensity and high ammonia and nitrate concentrations. Meanwhile, sites which had a good result are attributed to slight eutrophication pressures. With this, monitoring of water quality parameters and better watershed management in Minalongan Outside and San Miguel Inside will aid the recovery of coral reefs in these sites.
The successive increase in algal cover indicates a deteriorating reef condition. This observed coral-algal relationship, which leads to a decline in reef-building corals, is caused by natural and human disturbances in various factors such as temperature, sunlight, salinity, substrate stability, current, and waves, which are identified as limiting factors in the metabolic rate and reproduction of coral reefs. The optimal temperature to which coral reefs exist ranges from 25 to 30 degrees Celsius. At low temperatures, growth of corals is inhibited and can sometimes lead to death, while high temperatures can cause symptoms of bleaching, which can also lead to death of corals. Light influences the rate of photosynthesis. A decrease in the rate of photosynthesis reduces the ability of corals to produce calcium carbonate if there is insufficient supply of light. Salinity facilitates in osmosis of coral animals' living tissues, and with optimum salinity for coral reefs ranging from 27 to 40 per mil. Corals require a hard substrate, clean of mud that serves as a good place of attachment for planula larvae, which then grows into the coral animal forming a new colony. Furthermore, waves and currents are also important factors for supplying nutrients, sediment material, oxygen, and preventing the deposition of coral colonies. However, strong waves can destroy coral structures and disrupt coral communities. Drivers of coral algal phase shifts that greatly affect coral abundance and increases coral algal competition includes anthropogenic factors such as pollution, overfishing, water quality degradation, as well as natural disturbances like climate change, diseases, damages brought by tropical cyclones, and harmful algal blooms induced by storms.
To conclude, the Benthic community in Matarinao Bay is composed of 28% algae, 24% hard corals, 14% dead corals, less than 1% is composed of soft corals, sponges, and other fauna, and 33% is composed of the abiotic substrates. In particular, the dominant coral form is the massive coral attributed to its more stable structure. There are low coralline algae cover, but high macroalgal cover, which indicates degraded conditions. In terms of interrelationships, hard corals are positively correlated with coralline algae, but negatively correlated with macroalgae, turf algae, and algal assemblage. The unstable substrates, including sand and silt, covers the majority of all the substrates. The highest cover of unstable substrates was found in San Miguel Hernani. Stable substrates like rocks and coralline algae, which promotes coral settlement, only covers less than 1% of all the substrates. The mortality ratio in Matarinao Bay ranges from 0.2 to 0.6, with the highest CMI value in San Miguel and lowest in Bulawan Outside. The coral mortality index has strong positive relationship with the unstable substrates, but no significant relationship with the macroalgal cover. The highest chance of competition or bioerosion was observed in San Miguel with the lowest bioerosion ratio of 0.12. There are higher bioerosion ratios within all the MPAs, indicating lower competition between hard corals and other biota within the sites. The bioerosion rates has a strong negative relationship with the algal assemblage cover. In totality, the coral reefs in Matarinao Bay are in good condition. Coral reefs within MPAs of Dio Island and Bulawan are in excellent condition, and the other 3 sites are in good conditions. However, 2 out of the 7 sites, including San Miguel's inside and Minalongan outside, are in poor condition. Lastly, the possible major anthropogenic and natural disturbances affecting the benthic communities in Matarinao Bay include overfishing, destructive fishing, pollution, sedimentation, typhoons, harmful algal blooms, climate change, and ocean acidification.
Based on the findings of this study, the following are recommended. A. To conduct regular monitoring studies on, first, water quality parameters, second, to biotic factors suspected to limit coral recolonization, survival, and growth, which are recommended to show the environmental conditions of Matarinao Bay, third, to the collection of data concerning coral vulnerability in relation to climate change, which is recommended to further explain existing and projected benthic cover, and lastly, on the occurrence of overfishing, destructive fishing, pollution, and other disturbances from near coastal communities. B. To study further on, first, trends of benthic composition and coral cover over time, second, factors affecting growth of coralline algae, and lastly, the process of mediating the increase of unstable substrates, which are sand and silt. C. Study possible alternatives for stable substrates which are non-degrading to any of the benthic biota. D. Study and map connectivity within and between marine protected areas. And lastly, E. Formulate a management plan focusing on reef monitoring, restoration, and management which implement the guidelines in the concerned MPAs.
Marine conservation is recognized as a global priority. However, limited efforts have been made to evaluate the effectiveness of existing marine protected areas. As such, quantification of whether the conservation objectives are met as well as the identification of gaps are important in establishing systematic protected area networks. Thus, there is a need not only for studies that will provide baseline data to guide the implementation of management, protection, and conservation strategies, but also to evaluate existing ones. In line with these, the following management schemes are endorsed for consideration in the management and restoration of benthic communities in Matarinao Bay. Data-based management monitoring. First is to gather baseline data and time series data essential in assessing possible drivers of change in benthic communities such as climate change, introduction of invasive alien species, and anthropogenic activities such as overexploitation of resources, unregulated tourism activities, and development projects. Second is to conduct regular monitoring of both the biotic and abiotic components in the reefs to better understand interactions between them and how these parameters drive shifts in the composition of the benthic community. Third is to evaluate implementation of ordinances and laws regarding MPA management and make changes where necessary. Second scheme is community mobilization. The first step is to disseminate information to raise awareness on the importance of benthic organisms, its status, and the current laws implemented on MPAs in Matarinao Bay. Second is to remind constituents and stakeholders of their right and responsibility to participate in the management of the MPAs. Also, consolidate ideas on MPA management that would be both beneficial and non-degrading to the benthic communities. Third step is to secure funding for the implementation of comprehensive programs through revenue-generating activities and appropriation committees of the government, including Department of Environment and Natural Resources, Bureau of Fisheries and Aquatic Resources, the local government unit, and non-government organizations or NGO or private institutions. The third and last scheme is restoration and damage prevention. So the first step is to identify and reduce stressors that affect the health of coral communities to allow reefs to mitigate destruction and promote natural recovery. Then, execute restoration activities to rehabilitate areas through mapping and identifying habitats that have been degraded but can still be restored within a reasonable cost and effort. Third is to address areas with low stable substrate cover by affixing reef-compatible alternatives. And lastly, ensure a steady source of propagules in stressed areas within the MPAs in order to maintain balance between immigration and extinction rates.